Hello everyone, this video is a continuation of the topic of combinations. In this video we'll talk about using this counting rule with more advanced problems with more than one part. So in some cases we use the combinations rule with the fundamental counting principle. Now we would do this anytime we have two kind of separate groups of objects with no overlap between them, where we can't just lump everything together and count it all at once. So here's an example. Choosing a committee of men and women. At one school, the student government consists of 7 women and 5 men. How many different committees can be chosen with 3 women and 2 men? All right, so one thing we could do if you tried to group everything together and say, okay, well, we've got 12 people and we want to choose, let's see, 3 and 2, choose 5 of them. All right, well, the issue with this is that you may end up with one of those choices that actually has all 5 as either men or women. We have enough women and enough men that that's a possibility. So what we need to do is make sure that we have exactly 3 women and 2 men. Right? So we need to think of those two as separate choices and then just figure out how many combinations there would be altogether. All right, so if you see a problem with 2 different pieces like this, like women and men, or if it's a deck of cards and you're choosing face cards and number cards, 2 separate things, or 2 dice and you're choosing odd numbers and even numbers, right? Things where there's no overlap, then that may be a situation where you want to use the fundamental counting principle to kind of match up your 2 different options. All right, so what we need to do is use a combinations to figure out the number of women and the number of men and then put them together. All right, so we have 7 women and we're choosing 3. 7 choose 3. And then the number of men, we've got 5 men and we're choosing 2 of them. All right, so that gives 35 different ways to choose the women and 10 different ways to choose the men. All right, and then we need to figure out how to match those up together. All right, so if you think of the work that we did with tree diagrams, all right, let's say that you choose, we've got, 35 different options for combinations of women, ... all the way up to 35 different options. Now, each of those options could be paired up with any of the 10 combinations for men. So if this was a tree diagram, it would be like branching off from each choice of women into 10 options for choosing men, right? And what you end up with is this huge tree diagram with 35 different first branch options and then 10 off of each of those, or you just multiply those together, right? So we've seen when we did the fundamental counting principle problems, if you're choosing 1 from a first group of things and then 1 from a second, the way to figure out the total options is just to multiply. Right, so 35 times 10, there are 350 different possible combinations. All right, here's another one. On an exam, a student has to pick 2 essay questions from 6 essay questions and 10 multiple choice from 20. How many different ways can they pick the questions to answer? All right, so we need to confirm that there are exactly the correct numbers of essay questions and multiple choice questions, so those are our 2 things that we're choosing. And then we just need to figure out the number of options for each of those. So for the essay questions, we're choosing 2 out of 6. So that's 6C2. And multiple choice, we're choosing 10 out of 20. So that would be 20C10. All right, so the essay questions, there are 15 ways to choose those. And then there are a lot more ways to choose the multiple choice questions. There are 184,756 options. Right. And then to pair these together, we use the fundamental counting principle to say, all right, we should multiply these. And then that gives the final answer. There are 2,771,340 different ways to make this choice. All right, here's another one. See if you can notice a difference between this example and the last. To raise money for a charity event, a photography class plans to sell a calendar featuring popular pets owned by students on campus. They will need to choose 6 furry models from a pool of finalists that includes 9 cats and 6 dogs. How many possible choices are there if they want to feature at least 4 cats? All right, well, what's different? Notice the end here. We're not actually asked to choose a specific number of cats and a specific number of dogs. It doesn't say 4 cats and 2 dogs. It says at least 4 cats. So this opens up quite a few more options. We could choose 4 cats, 5 cats, or all 6 models could be cats. Now if it's 4 cats, it must be 2 dogs, right, since we're choosing a total of 6 models. If it's 5 cats, it must be 1 dog, and then it could be all cats but no dogs. Right? So what we have here are actually 3 different combinations problems, and we want to split these up into 3 cases, find the options for each, and then add them all up at the end. All right, so case 1, choosing 4 cats and 2 dogs. Well, we've got 9 cats to choose from. Oops. All right, 9 cats, choose 4. And then dogs, we have 6 dogs, and we want to choose 2. All right, so that's case 1, and then we'll multiply to find the number of options. In the second case, it's 9, choose 5, and then dogs is 6, choose 1. All right, and then in the third case, it's 9 cats, choose 6, and even though we have 6 dogs, we're only going to choose, we're not choosing any of them, 6, choose 0. Okay. All right, so now it's time to make the calculations. All right, so here we have all of the combinations. I've calculated these. And a couple things to notice that are interesting, and if you want to memorize these, this will kind of shortcut some of your work in the future. Anytime you have a certain number of things and you're just choosing one, there are only as many ways to choose those things as the total number. So if it was 6, choose 1, there are 6 different ways to make that choice, right? So, if you're standing there and, you've got 6 dogs in front of you and you have to pick one, well, you have 6 different options. Right? Same thing with 6, choose 0. There's a very limited number, and anything choose 0 is always just going to be 1. So this is asking, how many ways are there to choose no dogs out of the 6? Well, there's only one way to choose no dogs. You just do it. You choose none out of 6. There's no different way to do that, to choose nothing. Okay, and then when we have that, we can just do these multiplications. And we end up with 1890 and 756 and 84. Okay, and then we just need to add these up. So we've got the 3 different cases, and we end up with 2,730 ways to make those choices. All right, so one thing you might be wondering, why are we adding at the end there instead of multiplying? Well, think of multiplying as choosing different components of the same type of a thing. All right, so when we multiplied here in between the cats and dogs, that was because whenever we made a cat selection, we wanted to pair that up with different choices for the dogs. But now here at the end, we're not multiplying because we've already made our choices for cats and dogs. So multiplying is what you would do to kind of to pair things up. All right, that would be like choosing cats and then dogs, and then going on and then choosing more cats, and then going on and choosing more dogs. But we don't want that. We've finished all of the combinations. We just need to add them up to see how many there are in each of those 3 different cases. Okay, so there we have it. Let's do one more example. A 4-person crew for the International Space Station is to be chosen from a candidate pool of 10 Americans and 12 Russians. How many different crews are possible if there must be at least 2 Russians? All right, so see if you can do the setup. You might want to pause here and try this, and then I will give you the answers and we can make the calculations. Okay, so we have a case with at least 2 Russians. So that means that we can choose, let's see, we're choosing a 4-person crew. So we can choose 2 Russians and 2 Americans. We could choose 3 Russians and 1 American, or we could choose all 4 Russians and no Americans. Those are the cases. All right, so setting up the combinations, it could be 12 Russians, choose 2. And then we're pairing that with 10 Americans, also choose 2. It could be 12 Russians, choose 3, paired with 10 Americans, choose 1. Or it could be 12 Russians, choose 4, and 10 Americans, choose none. Okay, so here are all of the different numbers for the various combinations. And notice again, 10 choose 1. If you're choosing 1 out of 10, there are 10 options. And if you're choosing 0 out of 10, there's only one way to do that. All right, and then multiplying, you end up with 2,970 options, 2,200 options, and 495 options. And then adding those together, because we've got 3 different cases, and then we want to add to find our main case here, the case of at least 2 Russians. You end up with 5,665 different ways to choose this crew. All right, last thing I wanted to talk about, here's a table from the textbook Math in Our World, and this gives you a summary of the different rules for counting, and then some clues about which one to choose. So the fundamental counting principle is used if you're choosing a variety of different events in the main, kind of your main problem. So we looked at one with choosing paint types, and we had color and type and use for outdoor or indoor. So we had various options kind of within the main problem. We also said that the problem must be uniform. The events must be unaffected by the others. So if you see a problem that says outdoor paint only comes in 2 of these 4 colors, or some sort of restriction like that, then you back up and you actually don't even use any of these counting rules. You go back to some sort of a listing method. We talked about making tree diagrams. Okay. Fundamental counting principle, can be used with repetition or not repetition. So if you're choosing digits for a password and you can repeat them, all right, say it's a 3-digit password, then you can do 10 times 10 times 10. If you're not repeating, then it would be 10 times 9 times 8. But in both cases, you can use the fundamental counting principle. When you get to permutations and combinations, we're assuming that there is no repetition. No repetition. All right, so if you find that there is repetition, then that's your clue that you must use the counting principle. All right, so we've got no repetition. Then permutations, order is important, but combinations, order is not important. So those are some questions you can ask yourself. Is it uniform? Is there repetition? Are any of the events affected by the others? All right, and that helps you decide which of these rules to use. We talked about keywords for permutations and combinations, words that imply order, like arrange or things like that. And then combinations, things like choose, select, where order does not seem to be implied. All right, and then you have the formulas. I won't reread those for you. You know what those are. The other rule in here, the permutation rule for duplicate objects. All right, I think it should be fairly clear from the problems if that's the rule that you want to use. So we did things like the permutations for letters in the word Mississippi or things, or Massachusetts, things like that. All right, so we're trying to look at permutations or arrangements, but only the ones that actually look different. All right, so like different passwords, look for words that say like distinct, different, unique, things like that. Different, unique. All right, I hope that was helpful, and this is the end of the discussion on the counting rules. After this, we will start using these to calculate probability.